Knowledge of atomic model in solar energy is important for at least two important reasons. To design and optimize solar panels that convert the sunlight into electrical energy, and to develop new materials like semiconductors for solar panels. In this video, I aim to explain the atomic model focusing on just behavior of its electrons. I first here start to explain simply the periodic table and how the valence electrons are addressed in this table. I then focus on electrons, shells, or orbits, and valence electrons of few elements from periodic table. Atomic model suggests that an atom consists of a nucleus, which is made up of protons and neutrons surrounded by a cloud of electrons that orbit the nucleus. Here I'm going to briefly explain such model. The structure of an atom refers to organization of its subatomic particles, which include protons, neutrons, and electrons. The nucleus is located at the center of an atom and contains protons and neutrons. Protons have a positive charge while neutrons are neutral. The electrons are found outside the nucleus and occupy orbital or energy levels. These electrons have a negative charge and move around the nucleus in a cloud-like region known as an electron cloud. Why do electrons orbit the nucleus? The atomic structure is held together by the electromagnetic force between the positively charged protons in the nucleus and the negatively charged electrons. This force keeps the electrons in orbit around the nucleus and prevents them from colliding with the protons. It's worth to be noted that the energy of electrons in an atom increases as the distance from the nucleus increases due to the electrostatic attractive forces between the negatively charged electrons and positively charged nucleus, according to Coulomb's law. This law states that the force between two charged particles is proportional to the product of their charges and inversely proportional to the square of the distance between them. As shown in this figure, elements are arranged in rows and columns. According to their structure and shortly their chemical behavior. The rows of the periodic table are called periods. The columns are called groups or families and share similar chemical properties. There are 18 groups in the periodic table, each with a unique name and specific properties. In this video, I'm not interested in elements or transition metals in the middle part of the table shown in blue color. My main interest is only the arrangement of electrons, as I've explained the nucleus briefly in other videos related to nuclear energy. The most widely accepted atomic model today is the quantum mechanical model, which is based on the principles of quantum mechanics. This model suggests that electrons do not orbit the nucleus in a fixed path, but rather exist in a probability cloud or an electron cloud surrounding the nucleus. This model also explains the concept of energy levels and the sublevels of electrons within an atom. The electrons are arranged in shells or energy levels, with the electrons in the outermost shell called a valence shell with valence electrons, determining the chemical properties of atom. Let's dive into the valence electrons, starting from periodic table. Columns show groups that we can number from left to right by ignoring middle elements as shown. Here the numbers show both the number of groups and the number of valence electrons. For example, all elements in group 1 has one valence electron, and all elements in group 3 have 3 valence electrons. As an example, bromine has 7 valence electrons. This figure shows our shell model. The maximum number of electrons that each shell can hold is determined by a formula of 2n squared, where n is the principal quantum number of the shell. We now investigate the aluminum and would like to see the arrangement of electrons in different shells. We assume that the atom is neutral, meaning that positive and negative charges are in balance. The number of electrons is then equal to the number of protons, 13. For simplicity, we show energy levels as lines. We know from the periodic table that the number of electrons of valence level is 3 at n equal 1. Using this formula, we have 2 electrons. The maximum number of electrons in the second shell is 8. I define atoms with stable electron configurations as those with either complete valence shells or at least half-filled valence shell. An example of an atom with a stable electron configuration is neon, Ne. Neon has a total of 10 electrons arranged in 2 field energy levels with 8 electrons in the valence shell. This means that the valence shell of neon is completely filled with electrons, making it very stable and unreactive. On the other hand, an example of an atom with an unstable electron configuration is aluminum, Ai. Aluminum has 13 electrons with 3 valence electrons in the third energy level. This means that its valence shell is not completely filled or half filled, making it unstable and highly reactive. Aluminium tends to lose 3 electrons to achieve a stable electron configuration. This opens up a question that which elements in the periodic table do have tendency to gain or lose electrons? If the valence shell contains less than 4 electrons, it tends to lose electrons and create positively charged atom or positive ion. If the number of electrons in the valence shell is more than 4, it tends to gain electrons to become stable. Assume that we do not know the number of valence electrons from periodic table. How then we can fill out each shell? In atoms, electrons fill orbitals in a specific order, starting with the lowest energy level and progressing to higher energy levels. The first energy level can hold up to 2 electrons. The second can hold up to 8 electrons, and the third can hold up to 18 electrons. However, hereafter from n equal 3, we should be careful. Assume we select, for example, potassium K from the periodic table with 19 electrons. We set 2 and 8 electrons for the shells 1 and 2. We have then 9 electrons remained. If we use this schematic, we can place all 9 in the shell 3. However, we do not fill the third level like this. The third energy level holds up 8 electrons, and we then have 1 left electron that is placed in 5th energy level. In this regard, the potassium, by losing only 1 electron, becomes stable. This is called octet rule, at which the third energy level can sometimes, like potassium example, hold up to 8 electrons, even though it has the capacity to hold up to 18 electrons. As another example, we select calcium Ca with atomic number of 20. Finally, bromine Br with atomic number of 35. As shown in the table, with 7 electrons in its valence energy level. It can be seen that potassium and calcium tend to lose 1 and 2 electrons to become stable, while bromine tend to gain 1 electron for being stable. I've used the number of valence electrons in another video to study the conductivity of an element. By conductivity, I mean the ability of an element to conduct electricity.